Oh, I missed the on.
Okay, the Coulomb potential has a lot of properties that are a good deal more complicated than the oscillator potential. These are the two potentials that have a high symmetry. And we're going to deal with the Coulomb using symmetry now. What I have on the screen here is a picture of the hyperbolas that we ended the last lecture with. And the basic idea is that this diagram, the hyperbola pair that you're used to, just to turn that on its side a little bit so that this asymptote is level, is the key to a way to very quickly geometricize, that is, make a geometrical construction of all of the properties of the scattering. Now, this scattering we're talking about today, as I said, is an extremely important physics of phenomenon and a happening. It really changed the way we looked at matter at the atomic level and really gave us the idea of the atomic level. So what I'm imagining here is Rutherford's an original experiment of alpha particle has 2 protons, that's a charge of +2, and then 2 neutrons just to make the net mass twice as big. And he scattered that off through, basically had a very thin gold foil. But thinking at the atomic level, you've got to imagine if you were a gold atom, and in that lattice, you were seeing a huge number of those things. So this alpha particles coming in, going past most of the nuclei, and every once in a while it just gets close enough to scatter significantly off of a gold atom. Now the result of his experiment was that he didn't reach the nuclear radius. The nuclear radius of gold, 10 to the minus 15th, we've already talked about that. It's 7 times 10 to the minus 15th, so it is a big nucleus, but 10 to the minus 15th, it's a tiny number. Work out the energy, and I'll give a problem that does that, figure out just how close he got. And it's more like 10 to the minus 11th, so he's got another 4 digits there to go. So that he never actually got the scattering that would occur if an alpha particle grazed a gold nucleus. He would have seen that if he had, but that would mean an enormous amount of energy he didn't have. He was just using the energy that comes with the radioactive decay. And what we're showing here is a use of the formula that I told you should remember among all of the things that we talked about in the last lecture. Without our plus or minus sign, the relationship of the total energy and the Coulomb constant and the A parameter, the major radius of whatever you're talking about, ellipse, hyperbola, attractive or repulsive. We're going to treat all 3 of those cases today using the symmetry approach. But in any case, that formula right there is the key to drawing a circle with a diameter of 2a, which is the center of hyperbola pair, and figuring out what happens if you happen to have an alpha particle that's just dead on, that is, has 0 impact parameter. And the impact parameter is the key thing here, and this is be at 0.6 in the units that we're using for the geometry. So this is a typical scattering orbit right here. And the idea is to derive that with a ruler and compass. And as I say, I struggled with for quite a while teaching courses on this, when I realized, you really should be able to do that because of symmetry. I mean, there's got to be a geometrical way that's really simple. And it was just turning a thing that much that I could see that we have a circle here with radius A that will be used by all of the scattering. All of them have the same energy. It's isoenergetic thing, so it's the same A all the way up, all the way down for the scattering. So that's what we're going to talk about first. Then we'll get a little bit more into the symmetry that goes with that. So, zero impact parameter here, I've got this distance. Now, if I draw that same circle of radius A a little higher, let's have an impact parameter here of, say, 0.2 or something like that, just a little bit higher than 0, the construction begins by picking an impact parameter and then drawing a circle of radius A around a point directly above the center of the one that you had before. So that's the first thing. Ruler, you have. I usually make if we had more time, we would have you all with graph paper doing this. I'll have you do that at home. In any case, draw that, and then what we're going to draw is what I call focus locus line. Okay, all of the constructions we do today, they're based on finding the focus, and that involves writing down a focus locus and then finding another thing to connect with that. So that and then the next step right here is just to double this angle. And that's the scattering angle for the Coulomb. All of the things will be constructed this way. So the basic idea is you just copy this angle right here, the angle B, C, F, and strike off our ding line. That's your back. And this is the back scattering angle. We'll give other names to the forward scattering, other symbols for that. So basic idea is that's the geometry. And then all you have to do then is take a compass and strike an arc that is the length of alpha epsilon. And that will be the second focus of the scattering orbit. The main axis being tipped now by that angle that's determined by this triangle here. So I'll go ahead and dusty it up a little bit here, and then we'll take on a construction of the actual trajectory. Now that we have the two foci, that's a ruler and compass job. It's not too hard. So let's go ahead where this whole thing is a bigger picture, where we can do the scattering angles forwards and backwards. Make a little triangle that has them in it, and given the closest approach, that's the basic thing. So all of the scattering of this whole entire beam that's coming in is governed by a circle of radius A. Okay, closest approach here is about 1.4 in the units, the geometrical units we're using. So there's a B that's half of A right there, makes that angle. Here's a B that's 3/2. Now the impact parameter is that much instead of that much, 3 times as much, and the result there is a triangle that looks like this, a bigger angle, which I copied with the scattering angle, so now we have a scattering forward. And that's when you, instead of using a back scattering angle, we do forward scattering angle, so phi, Greek F, forward. This is all terminology that if you do any atomic scattering, nuclear scattering, any of that, you'll get used to them talking about these. So what I'd like to do is just quickly show what you do to derive the actual orbit. And the basic idea is that what you pick just randomly and do it as close as you can to this point without getting right on it. I'm just taking here a arbitrary arc, which I bring down to here. That's the first radius, and then the second radius is the difference between 2a and r prime. R prime plus 2a is equal to r. So the difference, r minus r prime, is going to be a constant for all of the orbits that we draw. So the basic idea is to find r prime and then use that radius on the second focus. So I would take my compass and just strike an arc. Well, I wouldn't have to strike an arc, I just go ding there and ding there, and that's a point on the trajectory that's going to be cruising up through here, touching that point right there. That's the closest approach for that trajectory, and then going on out the exit asymptote. So the rest of this, and I'm going to go ahead and do it on this screen that's a little brighter. You can see the geometry a little bit easier there. Then draw another arc, and if you want to be very precise, near the contact point you make the arc only a little bit bigger, but that makes r prime a little bit bigger, and you take that r prime and connect, and now you've got 2 points on the trajectory, here, and then on the exit trajectory another 2 points. So there's symmetry around this axis for this scattering event. Okay, and there's a couple more, there's a couple more, there's a couple more, and so on. And what you can see is we're not very far from the nucleus out here, but boy, we haven't been lifted much by that Coulomb repulsion of this gold nucleus, you see. And I'm going to show you some animations that show that rather convincingly. So anyway, this is a summary of the thing here, and the trigonometry of this is nice. If I just cover up the 2's here, what you have is the relationship between the forward scattering and the backward scattering. That's just pi. There's the forward scattering and their theta, and then the 2 of these together make the forward scattering is the phi, f, I'll learn it someday, and then theta here differ by pi, but when you draw it as a triangle, that's the triangle right there that we're going to use to finish this by getting a differential scattering cross-section. Okay, now before we go too far on that, I think it might be worthwhile to take a look at some of the animations. That's rule and compass is fine, but boy, it's really nice to be able to do all of this on a computer and have it displayed and run movies. So make a picture like that. But what I would like to do is go just a little bit further and do this one. I could do this one real quick. Let's just test this out because we're going to use both of these for things. I want to make sure they're working. So let's see if this thing is actually doing it. There it is. So there's scattering, just involving, and I've got a
20 paths.
There we are, right there. No, that's not
4
it.
down from that. Here.
4 down,
Yeah.
20. So we've got
Yeah,
20
I got
guys
to raise
here.
it to the top.
This is going to have a lot more. This is going to have a count of 200. Okay, so let's get that one going right now and see if it'll work on the other machine here. Okay, so it takes the computer a little bit longer. But notice, if I were to pause this thing, right there, it's hard to see much of a bend in that line of marching alpha particles. You can see a little bit of a dimple there, right? And that, I mean, this gives you some idea of the weirdness of Coulomb field. Okay, let's keep going here. Finally, you can see that it's getting repelled by the alpha. All right? And then, wow. I'll just pause it right there. Now, we're doing something else with this particular thing, is we're coloring the thing according to a color wheel where the Lagrangian determines the color. So we're showing you the quantum wave function for this. I'm doing it here too, but don't have a thick enough line so you really clearly see that. Now the other thing that I'd like to show, and I'll go ahead on this one to get that, and that means I'm going to go back and get the one just
You're
like
still
the
in the
one
finder.
we just, pardon?
You're still in the finder.
Oh dear, let's see if I,
You didn't switch.
there we go. Good. Okay, let me go ahead on this one. That's the picture. Now, a couple of things to notice about this. If you draw a circle at this point, that is, use these points to locate the center of the circle and then finish it and show that it's pretty close. Only here where it's peeling off of the envelope do you see much variation. And the center here is not at the focal point, not yet. It's approaching that logarithmically. You got to really wait a long time before the center of the circle settles on the thing that's scattering. That's where the alpha particle is. Okay. Now the other thing I want to point this out is that this is this experiment that was so famous in the small. While I was at USC, Darrell Judge was responsible for a NASA project that located this envelope, and they discovered this quite by accident. He saw the stuff that we were doing just with geometry and mechanics, and he realized that I think it was a Viking probe or something like that was sent from the Earth, and this is imagine the sun is right here and Mars is about here, and Earth is a little bit closer. In any case, the idea is that the solar wind, that's mostly light, but also many particles that are thrown out by the solar wind. But let's just look at this at the optical stuff that's coming out. The resonance of the Lyman-Alpha transition in hydrogen is what we're actually seeing here. And the reason this works, of course, is because the solar wind is a Coulomb field. That is, it's the force that it exerts on the whatever atom, in this case hydrogen, is being pushed is inverse r squared. So this model here, where we're showing a bunch of hydrogen, in intergalactic hydrogen, being pushed in a bow wave around the sun, is mind-boggling. Okay, that's really neat. I mean, it's just a lot bigger than the Rutherford experiment, but it's the same geometry. Okay, so I point that out, and then we'll talk some more about the geometry. And this is just sort of the logical contrapositive of our volcanoes of Io, right? Or the atoms at the National Institute of Standards and Technology that explode and form an envelope in some sense. So this I want to show you. Now let's see a case where we don't have an envelope, okay? And the way I'm going to get that one is I'm going to pause here, and I'm going to change the charge of the nucleus. Right now it's 0.2 positive. Let's make it attractive, okay? So what I'll do is I'll reduce that. Take me a little while here. TC's control here, which is, okay, now we have 0 charge on that nucleus. So nothing would happen in this case, but now I'm going to come down here and bring this, I keep getting off of there, down here to, I'm going to take it to minus 0.2, so it'll just be an opposite sign, and we'll reset t equals 0. Okay, here it goes. Okay, same deal, 200 or so alpha particles marching to war here with whatever it is at the center there, but this time they're attracted. Okay, so instead of having a bend form that way, they're going to start speeding up. Say, oh boy, wow, I'm getting into that Coulomb field now. Wait, come on, guys, let's go a little faster, right? Now it has to slow down because we have an algorithm in there that makes sure that your error due to big steps is not too big.
See, we lost one there. It collided, but...
Yeah, there is one that got eaten.
It's
Isn't that cool? So this is the opposite of that, but we don't get an envelope because they're all crossing each other there. And we'll see more of this at the end of the lecture that has to do with comet heads and tails feeling the solar wind. But I thought that you should enjoy playing with this particular app. Okay, now the patterns and things that you have in there are interesting, and if you want to see the wave function for this one, well, there it is in color. Classical chromodynamics, you could call this. Okay, I'm going to pause this so it doesn't eat up too much of our CPU, because we've got a lot more to do here today.
question, Professor Harter.
Yes.
The center of the circle for that one, was that just as far off?
That's a
to
good
the
question,
left?
and it's probably, I don't know that. Good
It's the
question.
opposite direction.
It was the opposite direction, but was it the same magnitude
Yeah.
for a given time?
If you got
You-
a feel for why
Yeah.
that's the case, if you have a feel for why that's the case, you might be able to answer
Yeah, go
whether
ahead.
the same magnitude.
See if you can find it. Yeah, you can use this app, or you can write another one that does this. But good luck, it takes a while to do that. Just use this one and see how it looks. That's a good question. I hadn't thought about that.
Same here.
Yeah.
See? That's
Yeah, good question.
what we want.
Yeah. The other part of this story that makes the envelope, makes this parabolic, shows that it's parabolic, is this. And the basic idea here that every one of this is the incoming asymptote for this particular case. It's a pretty big impact parameter right here. So it's going to cruise right up here. And at some point, it's going to contact this parabola that belongs to this kite. And the kite is there based on the basic idea of a hyperbola. The hyperbola that I'm talking about is this green one right here. That's the repulsive one. I just happened to sketch in there. It's attractive, the thing that's attractive to this. But in any case, the basic idea of the hyperbolic geometry, with this being the A epsilon, and this again, right there. So once you have that, you can strike off and get this thing right here, and then very quickly locate where another 2A is, right there, strike an arc all the way back, and then finish the kite. And then there's a smaller kite that goes with the actual trajectory, but we're interested in the kite that goes with the envelope being this red parabola right here. So I warned you early in this course that we would be seeing kite again, and boy do we ever see it for the things that involve Coulomb orbits, much more than the harmonic oscillator. But in any case, the other focus for this parabola, instead of being here and here, the second focus is at infinity, and that's characteristic of a parabola. So, just to give you a feeling for what the geometry of this is. This is a blow up of that that makes it maybe a little clearer. Now there is also that circle that oscillates with the parabola. Remember that was shown along with the kite construction back in, I believe it was chapter 9 of the review unit. If you do it very carefully with the graph paper and all that, you can make a whole bunch of circles all the way up, do a whole bunch of the curves that go ahead and make the envelope. But you can check this scattering angle formula using a protractor. One of the things that we'll be giving you for the next homework after Thanksgiving. It's a lot easier to do geometrical construction using graph paper with nice protractors on it. So that's what we've got here. And then you can check yourself to 3 figures. You can see a 71.5 showing out there. It's even a little bit more above 5, so it's almost a 4-figure construction, which doesn't happen very often in the geometry business. Anyway, I'm going to go ahead with this, get back to the original guide here. And the other thing that I would like to mention about this, besides the fact that other kites are involved here, this is the square kite right here. This is a case where the B is 2A exactly. And then if you make it less than that, then you start to make those Chinese kites. So here's the envelope only to that point. And the focal point is much closer together at this particular venture. All right, this I go for very quickly here. As I already mentioned, the deep space HM atom scattering was discovered by NASA in let's see what year was that we were involved in that. 1976, 77, 78, I guess it was, that we began to understand more about our interaction of our solar system with the hydrogen background. In any case, the scattering cross-section, particularly the differential scattering cross-section, we're talking about what's the difference between two particles that come in a path here, and in fact they cross, and then they have a differential polar angle, and they would have already a differential azimuth to go with that, which I'm not showing here. Out of the plane is the azimuth around this axis. Okay, the d phi isn't even mentioned here except at that point. So presumably this has cylindrical symmetry, so we can truncate that calculation there. But in any case, that triangle, the scattering triangle here, giving that, lets me take here a derivative of the impact parameter, the B parameter of all of the hyperbolas, and differentiate that with respect to that polar angle. In other words, how much of a change do I get in that thing compared to what I've done here? And that's all there is to what's called the differential scattering cross-section. What's really interesting about this, I won't stop and go through all the trigonometry on this, but the steps are all there. This classical result matches the quantum first-born approximation, which is all most people do for quantum Coulomb differential scattering. So that is an interesting thing as well. So here is where a completely classical approach comes up with a number very similar to what the quantum mechanics gives you. And also this is where we realize that the Coulomb field has infinite total cross-section. And you can see that this parabola is not going to stop. It just keeps on getting bigger and bigger until you just get tired and don't bother to make anything more with a bigger impact parameter. But if you had a beam that was infinitely wide, it would all get scattered. And that's you can see that if you integrate this monster with a negative 4th power sign, a big fat infinity is what you get. If instead you integrate the geometry of a hard sphere, okay, that's more like the kind of scattering people are used to, and it better come out 2 pi r squared, and it is kind of fun just to see that one, compare it with the other. So I'll go ahead and see if that runs for us. Yeah, here it is. The same program, so you can get all of these programs. So there's the hard sphere. It hasn't done anything until there. Now, your question might be, where's the center of that circle? Looks like it's right about there, doesn't it? In any case, there's some really elementary scattering going on there. Okay, and the cross section is very finite, unlike Coulomb. Coulomb's a monster in that regard. All right, let's see if there's anything else I can mention here. I think that's enough to get us started, because this is cool. I mean, cool for someone that loves symmetry, and I would hope that you share some of that love with the amazing, absolutely incredible eccentricity vector. That's what we're going to go on to. So this is going to let us calculate with a ruler and compass absolutely any Coulomb orbit. And it's very powerful. But it's also powerful in just doing the algebra, and we'll do that too. In any case, one of the things that's true for any isotropic potential is that it will conserve angular momentum. And I'm now using the letter L, big fat L, it's a vector, for the r cross p angular momentum, mr to cross r dot. And orbital momentum, you see. What have we been using in the last lecture? We were using mu for this. And we'll come back a couple of times with formulas from the previous lectures with the letter mu in place of the L. But in any case, the idea is, and this is at first quite magical, and that is that this Coulomb field is unique in that it preserves the direction of this vector here, P cross L subtracted from the unit R. And P cross L is P cross R cross P. That's nicely reduced, as we'll do here. But I want to make the comparison between this extra conserved thing, and this is for the Coulomb field outside of the Earth, and now back to sophomore physics Earth. Inside the Earth we have the three-dimensional, actually, but we've mostly kept the two-dimensional isotropic harmonic oscillator. And we've been working with the Stokes vector for that in the last few lectures, right? Well, the IHO conserves this vector, whereas the Coulomb conserves, in addition to angular momentum, they both conserve angular momentum, any angular momentum, for isotropic things. So these operators here, if you take our group theory course, you will learn about that being U2. You already seen most of that. Well, this one is the symmetry that goes with R3 cross R3, which is orthogonal group 4. That discovered much later. What is known in the literature is this vector epsilon times km. And this is, I learned about the vector A. This is called the Laplace, Hamilton, Gibbs, Runge, Lens vector. And I think there's a couple more names that go on that one. A lot of people discovered this. All right, now, is that hard to discover? Yeah, you'd think so. What do I do? Just take the P's and R's and put them together and try to get something that's conserved? It's a lot easier than that. Once you get this vector and just get rid of that km, you get a vector that's magnitude is the epsilon, our eccentricity. So I call it the eccentricity vector. The heck with this A. That's great for group theory, but let's just do the geometry. okay? If you take epsilon and dot it with a radial vector, just look at the components of it, or dot it with a momentum vector, we're going to do both here. But this one, this is quite remarkable, because what I'm going to be getting here is r dot the unit r, that's fat R over the magnitude of R, okay, and then I've got this P cross R cross P, I've got this P cross L, R dot P cross L, and all I have, I know I can switch the cross and the dot, right, and then I just get L squared. Ooh, I think we're recognizing something here, okay? Now, crossing with P, dotting with P is really simple. You just get P dot R over magnitude of R. That is, you get the rth component of momentum. We'll worry about that later on. But this just gives us the equation for the ellipse. That's absolutely just gorgeous. Yeah, this is our equation for the ellipse that we got in polar coordinates. End of proof. Right? You don't have to struggle with all the group theory to show that this thing commutes with the Coulomb field and with the angular momentum and all that. Okay, so here it is. There's our, and the thing is, this takes care of all conics at once. That's even more powerful. Okay, so here's where mu squared went in our stuff in the last couple of lectures. All right, here's the lattice radius, lambda. Okay, which is popping up here. That happens to be it right there. And there's a perihelion, and then there's the uphelion right there. Lambda over 1 minus epsilon, lambda over 1 plus epsilon. We're going to work with all that stuff again. Except now, not just the ellipse, okay? Not just the attractive orbit that you get at low energy for around a focal point that has a second focus, and we're going to play with the symmetry of that very soon here. But the basic idea is here is P cross L. If that's P, the angular momentum, linear angular momentum, linear momentum right there, that's the P cross the angular momentum, and then there's R. You kind of see how these things go together. You see, this P cross L, that's part of this thing makes sense. There's P cross L divided by the constants, Coulomb constant and mass of the particle that's orbiting, right? So this is the case for K greater than 0. Our convention is that's attractive with Coulomb, okay, and energy is less than 0. That's bound energy, ellipse, okay, and this eccentricity vector doing very well for that. But then if you start stay attractive, but get your energy up, when you throw this thing by that point there with a lot of energy, it's just going to go out and get on a straight line as an asymptote to a hyperbola. So this is the hyperbolic. That's E greater than 0 rather than E less than 0. And again, the P cross L is there, the P is there, it all makes sense. This is giving us an epsilon vector. You see, this is a shorter epsilon vector, this is a longer epsilon vector, but other than that, we're home. So that takes care of the attractive orbits. We still have the repulsive orbits, but they don't make ellipses, they only make hyperbolas. And now the interesting focus is on the other side. You see, for this one, this is the thing that's doing it attractive, and there's nothing here. This is vacuum, right? Nothing going on there, except the base for the epsilon vector. But that's mathematics. Physically, there's nothing there. Or here, nothing here, okay? It's all being done by that point, all right? Now the nothing is inside the curve. The thing that's pushing is repulsive, and it's sitting here. Okay, so all three of these are being taken care of. Their geometry, their physics, their everything by this magic vector. The quantum mechanics with the A, the classical mechanics with the epsilon. Okay, does that make some sense? All right, just to go through it again here. Three things. Now, when you read this, you can click ahead and take on momentum early. It's on page 81 to 104. I hope we get time to do that, because that as you remember, is a spectacular effect of a Coulomb orbit that the momentum traces a circle, an off-center circle. So we got to prove that. We haven't proved that yet. But the epsilon's got that buried in it as well. Now these are pages from our last lecture. This is 25. We're in 26 now. Page 78, 79. This is 78. Just a reminder. Now here's the angular momentum again. Now as a mu. Okay, so formulas like these that are completely derivable from the epsilon geometry that's we're about to do here. And there's that physical table putting the parameters A and B that are the Cartesian XY parameters. These are the physical constants, energy and momentum, L or mu. And then here is something that has to do with L or mu. That's the lattice radius, same sort of letter, Greek, lowercase l maybe. And then the epsilon here, right here. That's the most complicated function of them all. But in terms of the Cartesian coordinates, it's not that complicated. So 6 of one, half a dozen of the other. That's the fight that we are playing here between polar coordinates and Cartesian. We use them both sort of easily with this epsilon vector. It's this dot product with R that gave us the equation of the whole ellipse. But the dot product with P, that we need because we've got to get some familiarity with what the linear momentum P does as it goes around the orbit and makes that magic circle. So what you discover here is that when you dot this thing with P, this just completely disappears. All you've got here is P dot vector R over magnitude R. Well, that's P dot a unit R. In other words, it's the rth component of the momentum. And what it's telling us is that that thing is, and the epsilon is always defined by the x-axis, that thing is epsilon times the x component of the momentum. What does that tell us? Okay, well here's a typical point on an orbit. Presumably if it was going this way, that would be the linear momentum tangent to that. Okay, that's good. Now that you can draw back. You can draw back a dotted line to the extension of the radius vector, okay? And you can call this the x component of P right there. It's the x component that's pointing in the same direction as the epsilon vector. And then there's this one, which is, well, you can see that that vector is shorter because epsilon is an elliptical epsilon and therefore less than 1. This one is about 0.9, 0.866. It's exactly the square root of 3 over 2 in this case. Okay, so that's about what you have. And if you indeed will put a whole bunch of these things up here, I'm going to go ahead and do it on both screens here so we can make some comparisons. Here's a whole bunch of them, and particularly that last one is of interest, just to get some idea. As I go around this circle here, I can always strike a little light blue. You see that little light blue arc. So there's the 0.866 right there. Okay, just a little bit shy of 0.9, which would be about there on the P line, the momentum line. Now, one of the things that's not being shown here, we're drawing this P the same size. That's wrong. Okay, these vectors P and minus P are not drawn so they correctly show that momentum grows as the radial distance falls. And boy, does it grow. And we got to see that. That's really a magnificent effect. Much more spectacular. Many of these things are much more spectacular for the Coulomb than they are for the harmonic oscillator. But we pay for it in complexity. Okay? And here, of course, is an interesting one. This is still 0.866, this arc here. Of the length associated with the radial component of this particular point associated with the tangent vector that is the momentum, and then the x component of it is right here, and this is 0.866 of that. Okay, well, can we make some hay out of that? This is what you always try to do in this business, and here is a neat way to do it. with Thales circles, that is rectangles in a circle, each one of them a circle of diameter p and having a right angle, no matter where you draw the point, but we're drawing the points according to where the radius is pointing, and the component of that is going to be epsilon px, and then where the PR prime, and that's the thing, there's another radius here, okay? We didn't talk about that radius, but epsilon knows how to handle it. It's the same way. It's going to be epsilon px2. Both of these are going to be the same. And what we have just proved by doing that, and we can do it some more, at any point, the p's, and again, I'm not making the distance from the perihelion influence the size of the p. I'm just showing you that there's a symmetry which demands that the bisector, that is the bisector of these two p's, points perpendicular to them. And I challenge you to quickly prove that just from the ordinary geometry of the ellipse. It's sort of ugly any other way. This just gives it to you for free. So that is important. The bisector of an angle between the two kinds of radii is normal to the tangent vectors in this case. Okay. And what's neat about that is it works for hyperbolas too. This isn't just for the ellipse. But now the p is right along the hyperbola. Okay, it's tangent to the hyperbola, and it's bisecting. You don't need another circle for this one. Just that's it. Okay, so we got to use that. That's what we're going to be using here to make some sense out of the momentum. All right. Now, this is the pièce de résistance, the resistance of this lecture. It's the cool part, I think. And this is a geometrical construction using the epsilon vector that allows you to, with a few steps of ruler and compass stroking, at any orbit at all, any Coulomb orbit at all. Okay? So the next several pages are going to go through just 1, 2, 3 steps, basically. Then we'll use analytical geometry of the ellipse and the epsilon vector to prove what it is we're talking about here. Okay, so let's get this queued up here. There's the first step. First step, it's imagined that you have picked a radius from the Coulomb center, and you've decided to launch a particle with some angle and some speed. So the idea is to figure out the orbit you're going to get if you shoot something from any point. Okay, so the first thing you do is you define an elevation off of the radius pointing to the center of the Coulomb field. And then having picked that, we do some other tricks. Basically copy angles a few more times. Okay, so that's the beginning of this. The second basic step, looks like there's more than just a step. It's kind of a family of steps going on here. And that is, you copy this angle. If you copy that angle, gamma, and then draw a line through the point of launch, you get the focus locus. Okay, remember there was a focus locus for the Rutherford scatter. There's a line that we found going through the 2A circle. Well, this is the same thing, except it's off of any radius with any direction that I want. I just have to make sure this angle is the same as that angle. Okay? Now, why is this the focus locus? Okay. We know this is a focus. So the question is, what happens when I come up? Let's imagine I have a ray of laser pointing at this line, and it's a mirror. Okay, I will go boing, That's why I copied the same angle, to get that. I want to get this to have another focus somewhere on it that makes the orbit that we're interested in. Okay, it takes two to tangle in this thing. Whether it's a hyperbola or an ellipse that we'll be making, the only time these two foci are together is when you have a circular orbit. That's trivial. So the job is to find where on the focus locus that focus is. And that's the third step. Okay, is this following fairly closely here? Okay, well, that's what you do. That's the finishing of it right there. Okay, basically what you do is you take this arc or this line and copy it down here. Basically, you're constructing a perpendicular to that point off of the momentum launch line, the P line. Okay. Once you've done that, then it's just a question of figuring out how much energy you gave this guy. How long was this P vector? Okay. That's the final deal with this construction. So basically what we're going to be finding here is the epsilon vector. All I have to do is tell you what R value, that is the ratio scale of kinetic energy to potential energy that you launched that thing with. Okay? And you got to get the sign right. If this thing is attractive, you better have a minus sign. And if you don't want to fly off and leave, not have an elliptical orbit, you better stay in this region right here, between 0 and -1. So all of our elliptical orbits are going to be found by putting an epsilon vector through one of these points, and it will point to the focus of the orbit that will do that. So that's the end of the construction, basically, right there, for getting the focal points. Now the R is the initial KE over the initial PE. That's weird, right? This is not a conserved quantity. This is just an initial condition quantity. But that is mv squared over 2, kinetic energy, initial V, and minus K over R initial. Okay? That's what we'll be feeding into some analytical geometry just a few pages ahead. So when you come back and study, just click on that and you'll get there. Okay, so that's the basic idea. Let's just go ahead and see how this works. If I can get this to work, okay, if I decide that I want to throw this thing with an R of -3/8, okay, well, if I've made this little scale here with 3/8 on it, okay, and that's right about there, I go ahead and I draw a line through that to there. That's the focus of the ellipse that's going to have that R ratio, that energy ratio. And it keeps the energy. The total energy is kinetic plus potential. That is, the sum of these two is constant. But the ratio is what gets you started. Isn't that cool? It makes me sneeze too. Okay, when I first discovered this. So first I wrote a paper on the on that thing that had to do with Rutherford scattering. I was surprised at it, except I thought everybody knew this. They didn't. And then I said, hey, can we do this with any orbit? And I did that, and the next paper came a couple years later. And this was while I was in Brazil. Didn't have anything else to do except go to surf on the beach and whatever. Anyway, this is neat. So here's your -3/8 ellipse. What if you want to have a repulsive orbit? You got to go up into this region right here. It'll be a hyperbola, guaranteed. Or you can point the thing, way down here where your other focus goes to infinity. That's a parabola, a really high energy parabola that goes out and never comes back. And then you can just keep on going, tip the thing this way, so that you intersect the focus locus up here, and that's attractive hyperbola. I mean, the geometry of this and topology of this is really quite mind-boggling. And so here's another example here where I'm pointing into this region right here, and I'm making a repulsive hyperbola. So that's what I'll be making until I crank the energy up, crank this thing way up here, so that my line is right about there. That's what I'm talking about, infinite energy. It's right there, infinite positive on this side and infinite negative on just the other side. It goes with all the negative guys that are down here, but they have come back out to that side. So this is weird, but it does them all. So this focus locus for k less than 0, remember, that's repulsive because we have a minus k over r. Okay. So that's repulsive, and it will have to have energy greater than 0. So as long as you stay at, your focus is in this neighborhood, okay, that's what you're dealing with. As long as your focus is in this neighborhood right here. It doesn't matter how fast you go, it doesn't matter how fast you go, infinitely fast, and that will be a focus way the heck up there. Okay, so that's what I want to show. I want to now do the geometrical proof that this works. Okay, and I happen to pick a repulsive case, r equal plus a half. Okay, and let's see if there's anything I need to say about the minus a half, minus 3/4. And this is a linear scale, by the way. Okay, so we've been talking about r plus 3/4 right at that point. Okay, see if there's anything. Yeah, but this whole region of the focus corresponds to k greater than 0 and e less than 0. Okay, so we're talking about attractive orbits all the way down to there, and these are energies less than 0. The positive sign, that's hyperbolas. These are attractive, unbounded orbits. They're hyperbolas. Okay, this is everything above this point is getting is participating in that. This red region right here, focus, all the foci in here correspond to k less than 0. It's repulsive full on field, and that has to be e greater than 0 in order to do that. Okay. And that's what we're working with right now. That's what this thing here is. It has this focus and this focus, and that's its main axis, and it's symmetric around that. Doesn't look like it. Yes, this is a little longer than the other. Okay, so that's the deal. Now, remember what r is and what is the initial velocity divided by the escape velocity squared. Okay, that's another way to say the r in terms of velocity, okay, instead of kinetic energy. So, here's the epsilon vector dissected into just ordinary algebra. The cross becomes a sine of a gamma angle of this angle. Okay. And then P and L appear here as a product divided by Km. So there's the epsilon definition. Here we're taking it apart. Okay. And then we go ahead and use some trigonometry. We're interested in these coordinates here, 2r sine gamma, 2r sine gamma this way. Let's see if that way. Yeah, this number right here is, if I to I think, and we'll got to be a little careful about this factor here. This is what I'm doing. I'm taking the mv squared. And I've got 1/2, so I put a 2 there. That makes me have ke there. And then I've got here minus k r0 in the denominator. That's the other r. This guy right there. So there's your ratio right there. So it's the KE-PE ratio is the scale factor with the 2 sine gamma on this axis here. So these things are all scaled to the KE over PE, but it's 2 sine gamma scale. That just depends on what angle you will make this thing big or small by changing that angle of launch. Okay, and then we go ahead and do the vector analysis. Just put that epsilon together, 2 sine gamma in the coordinate system involving this vector right here and the R unit vector. So at any point I have an R unit vector, that's our launch position, and then we have this P cross L axis. This is a unit P cross L axis right here, and that axis is getting a 2 sine gamma scale factor. That's it right there. So we're tipped in a coordinate system where this is the y-axis. That's the y unit vector there, with the ratio multiplying it. And you put all that together, you get that 2r plus 1 factor. So for a gamma of 45 degrees, which is kind of what I have there, I get 1 over square root of 2 components of that vector in that coordinate system. And you can see the parameters are what we say they are. So this effectively gives us a proof that this construction works. And it's just based on what the eccentricity vector is doing. And there it is, a really big eccentricity vector, big enough to make a hyperbola. Okay, okay. Now, this is all stuff that's automated. So if you want to mess with this thing, you can do it. There's a just by, and I'm going to drop ahead here just a little bit. Here's something where you go ahead, when you get to this thing, just play it, and it's just showing you what's going to happen when you use that thing. Basically, you have control of what you set the momentum to, what you set the epsilon vector to. You'll see the focus locus moving, okay, and then when you stop and click, you'll get an orbit that goes with that. So this is really a cool way to set initial conditions on a computer. This is a very cyber geometrical construction. No rulers and compasses, it's all silicon. Okay, so I point that out. Now I'm going to go ahead and just run a particular case, and this will set the stage for the momentum. As you can see, the momentum gets really big, even for this medium eccentric hyperbola. Okay, and the idea is that I can go and just move this thing around and make all kinds of crazy initial conditions. I turn them inside out, doesn't matter. Usually it gives you something that works. You can see where the initial velocity is. It's right along that p vector. You can see where the other focus is. The one that's in the middle of the screen is always fixed. So what I'm going to be doing when if I'm not careful, I'm going to make something that flies away and never comes back. But there's a typical situation. I'm going to be making some kind of ellipse that's pretty circular. And then it goes, it's slowing down as it goes to the high part, the aphelion, and then speeds up a little bit around the perihelion. So be my guest. This is something that's really lets you get a feeling for this epsilon construction without, let's just face it, ruler and compasses, some people love them, most people don't. So you've got an electronic one here. Now, this is ticklish. This is a very algebraic way to handle the description of not just the position, but also the momentum. Now, you've got to realize the difference between these two major fields that have high symmetry, the oscillator, particularly the isotropic harmonic oscillator, which is just p squared plus r squared, and this Coulomb thing, which is p squared plus 1 over r, right? Potential 1 over r, right? It's got a big singularity right there in the neighborhood, okay? The Fourier transform of the oscillator is really simple. P squared plus r squared just turns into r squared plus p squared. P and r are both squared, so that's Fourier transform. P becomes a variable instead of a parameter. Okay? This is different. the Fourier transform of the Coulomb problem is, it's so onerous that no one shows it. You gotta go to group theory book or something to see that. Okay? So I want to make that clear before we go here. Now, this is our radius function. This is our mu, angular momentum. We're using the standard notation for the angular momentum mu that we've been attaching to Coulomb description so far. Okay, but there they are. Radius and angular momentum are the main characters in any of the discussion. And what we're after is the actual momentum. That is the velocity times the mass. This thing, we need a formula for that. So we're going to fill this screen here with the algebra that goes with that. And then we'll come back and animate some of the things that have to do with that. So let me go ahead and do it on both of these screens, since it's a bit of a slog. Okay, I could have made a couple of equations shorter, but and I used to have, and I just must be getting old, I've completely forgotten a really elegant proof, but I'll show you how I think you could reconstruct that at the very end of this. So there'll be a geometrical story to go with all this algebra. In any case, here's the phi dot that comes from this, and then I take the 1 over r squared, I take 1 over this guy right here, so it turns into km over L squared, and the 1 minus cosine comes up in the numerator. So we need the phi dot in order to get x and y dot, basically. And then r dot is here. So here are the two velocities in polar coordinates. We're going to try to see if we can get back to the Cartesian coordinates just using that. So I take that derivative and also multiply r by phi dot right here to get L over r. Then I use that 1 over r again right here to get something that looks promising. I've got an r phi dot equal to that thing. Then I've got an r dot that's not too bad. If I go ahead and finish that, it's a sine over 1 minus cosine squared. So I go ahead and place this 1 minus epsilon cosine squared, this guy right here, in that part of the equation. Use this guy again to get the scale factor. So I end up with an r dot that's not too formidable. It's just a minus k epsilon sine phi. At this point, you could probably turn that around into something that's going to be the construction. Instead, I just continue the Cartesian algebra here to get xr cosine phi and x dot. That's got two terms in it. And y equal r sine phi, polar coordinate conversion, to y dot. Again, a combination of r dot and phi dot. Okay? Well, we're almost done. There it is. Basically what we've got is r phi dot up here is that thing. Bring that down to right there. The pink, that's the angular part is the pink part, and then the radial part is the light blue. Okay, there's the r dot right there. And a lot of things cancel. This particular guy here, well, I'll just go ahead, do it one more time here. Let's get both of these going, okay? This guy down here gets to use sine squared plus cosine squared, actually minus sine squared minus cosine squared is minus 1. So that makes that one pretty easy, times epsilon. Epsilon's in there. And then the cosine comes out very nicely right there. And then this one does a similar thing with a sine. So if it weren't for epsilon, this would just be a circle around the origin. But with the epsilon, it's a circle somewhere else. Okay? And that's what we've got to see geometrically. That is a bit of a chore, to say the least. But there's what we're after. Now we can see that That's why the momentum tracks a circle around some point that's not the center of the circle. That means it gets going fast on that circle at certain places and really slow some others. So let's go ahead and use the epsilon construction to plot here a day in the life of the momentum and the orbit as well. The whole shebang is what we're after here. So I'm just going to click through this thing one frame at a time. We start off with a little tiny p right here. Okay, it's going to be a great big p over here. All right. So apogee, smallest p. Okay, and these are the equations that we just derived. Okay, just so you see the algebra on top of the geometry. Okay, so we're doing that thing with the Fayetteville circle and the p. And now the p's gotten a little bigger. And here's my R scale, the ratio scale. Okay, that's what it is. It's part of it goes in a big circle. It's a chord in a big circle, as you saw when we just did the thing before as a simple example. Okay. And the thing is that scale bisects the that is, it bisects the angle between the big radius and the little radius, and always will. As we cruise up here, getting a bigger p, that thing's going to follow. Okay, so let's put that one on that screen and put this one on this screen. Okay, now it's more like what we saw before, a reasonably sized scale. It goes from -1 to 0. So we're talking only about a bound, attractive orbit, an elliptical orbit. Okay, and then here's the p vector. Now I'm only showing one side. The momentum, obviously, time reverse could go the other way, has that symmetry. Okay. Well, put this one in that position. Go to this one. Now we're right at the at the point of we've fallen this far, but we've got just as much distance to go. Now the p has gone from being that big to that big. We're only halfway. Right? It just keeps on getting bigger and bigger, and now we start putting some more geometry in there just to be fancy. And I can show a number of things here that I'm not going to bother to talk about. But basically, the p vector that I'm drawing off of the r vector needs to, actually I'm drawing it off of here, it needs to be taken back and put on the tangent. That's a bit of a construction right there. But other than that, we are getting a geometrical construction of the p vector. And you can see the r scale with this particular configuration is getting pretty small until finally, there we are. That's the maximum p. Remember, it started this big, and now it's that big. So you're talking about a ratio here of this to that, right? That's what you're making your p bigger, right? Don't need that. Don't need this construction to tell you that. Okay? So that's it. And of course, there's a typical calculation showing you the p vector
I gotta change the
tracing
color.
a circle. On an ellipse that's not terribly eccentric. And I'm showing I'm looking at obliquely, so it looks like an ellipse to me, but this is just a shortened version of the p vector with its rear end attached to the origin. So it's not too different in terms of getting really big and then getting really small from this construction here. Okay? All right. Well, there's I'm going to take a little bit more time than we usually do, because I want to just let you see some other things that you can play with on your own that have to do with astronomical phenomena like comets, or some weird things that happen in charges and solids. First, I want to sell this, that the parameters that A and B are great for Cartesian, but that angle gamma, initial R, also a good parameter. So there's a whole bunch of stuff that lets us make connections with those parameters. And you learn a little bit about what are the limits, what's the topology of these orbits, these orbit parameters. And these are ones that the R gamma is a pretty neat way to handle that. So A and B are related in a very funny way to gamma and ratio R. And that's worth knowing about. And then here's some of the geometry that shows that. And then here's some graph paper that we'll be using. This is graph paper from that paper. But here's the other thing that we haven't shown yet. And that is the envelope that's formed by an explosion in an attractive Coulomb field. Okay? And I'm imagining that's the orbit where the attractor is. And I'm throwing an ellipse, just one ellipse, for a particular initial momentum, either this way or that way. What you're going to see here is that this is, it looks like the ellipse that you get when you let an explosion go in the IHO. But boy, is it different when you actually see it animated. And this is something you might not have discovered without doing a computer study of this thing. So that's what I would like to really show you. In any case, this is something that's in the textbook, that description right there, and then those are examples that I would like to show you. So this is the one that I'd like you to see in motion. It's really hard to tell what happened during that sequence there, but let's go ahead and see what it is that happened. It takes a couple minutes. Boom, right here. There's the attractive charge. Okay. Well, for a long time it's just a bunch of dots, and we have a fair number of them going here. Always have to, we have 201. So at first it's just kind of a lopsided sphere. If it were coming out of the screen, we would be doing that, but where everything's in the plane there. And there it goes. It's doing that attractive Rutherford off of an attractive point. And it's slow because the computer has to recalculate. It's slow, and it makes that loop-de-loop that you saw in the Rutherford attractive thing. Okay? And this is assuming, of course, that none of the particles got lost right there. One of them did. You can see there's a gap now in the lower part of that circle. So these guys really going fast compared to these guys aren't doing much at all. They've been going boom outward, but they're starting to slow down. And you can see this is really weird. The harmonic oscillator, remember, it went boom, unboom, boom, unboom, right? This is much more complicated than that. As you can see, now we've got two ellipsoids of whatever you want to call it. And they're going to, nothing in this thing allows these to talk to each other, so they're going to go right through each other. Each one of these things go right through each other. And we're now halfway. This thing has to unwind. How in the heck does it do that? Well, these guys are slowing down. They're way out there. they're at their uphill end of the envelope and also of their own trajectories. These guys are speeding up now. And they're going to do an unloop. Going faster and faster and faster. They're going to go right through the region that has the attractive charge. And obviously this is very idealized because they're not going to get lost, at least not much. So there's the loop-de-loop undoing. Isn't this amazing? I mean, this is all the things a Coulomb field can do. And it slows down now because it has to make the step size so that energy is conserved. Gosh. Now we're closing down. That loop closes.
Try now.
We'll stop right there, and you can guess what happens next. Okay, I'm going to finish now, just with a couple more points. A comet head, if it was perfect, if the gas particles coming off from the solar wind, be a Coulomb field. A comet head, was that a simple model, would be a hyperbola. So now we have an envelope as a hyperbola. Okay. But that hyperbola can be weird. It can also be concave. The thing is really expanding around that repulsive charge. You get the Rutherford. But it isn't a parabola anymore, it's a hyperbola, a concave one. Okay, that's kind of neat. These are all ready to practice. A comet could be a plane, bisecting the distance between the source and the repulsive solar wind or whatever. Flat comet, no one's ever seen something like that, but in an ideal situation in an ion chamber, would have that. Okay, I'm going to stop. This is the paper that we wrote that has all the little ways to do this. And then this is the day we never thought we'd have all this graphics, so I was making things that would allow you to do it on overhead projector. And I was thanked for that, but not for long because that's pretty clumsy compared to what we've got here. Okay, well that's Coulomb. I hope that it does something to help your digestion for Thanksgiving. There's Coulomb fields all over the place in your eating. So we'll come back and we'll be talking about rotations. Make sure you put the Unit 6 in your textbook, and we'll be doing small parts of that. We've already done the Euler stuff. So there's some other things that we need to cover before we finish. Then it's relativity and quantum for the last few lectures. So, okay?